Last time we did Rutherford scattering. I just want to review what we did and what it's all about, because I think it's a beautiful derivation. And then you can actually tell people that you actually did it. Now we're just not just giving the equation. That's not really doing it. Okay. The idea is you have one charged particle coming from infinity towards another one that's fixed at the origin, and through a Coulomb repulsion, the one moving will be deflected. And the question is, what is the this deflection angle, theta, also called the scattering angle? And we did it. First of all, we noted that at infinity, the total energy is just the kinetic energy, given by 1/2 mv naught squared. So the speed will be v naught. And because of energy conservation, as it comes in and gets deflected at infinity on the other side, that speed must also be v naught. Second thing we noted is the repulsion force will have two components, one in the x direction to slow it down, and the other in the y direction to speed it up from 0. So initially it had no y component, and then eventually it does. So if you take the integral of the y component, initially it's 0, afterwards it's v naught sine theta. This integral is also the acceleration over time, because this force is a time-varying force, right? It changes in time, so the acceleration will change in time. And all we have to do is integrate this to get the speed, and that was our strategy here. And you put in for the force, the Coulomb force, you get this 1/r² term. The sine phi it's the y component. And then the clever trick was to note that angular momentum is conserved. Michael, you're seeing this the notes I'm showing, right?
Yeah, I can see it.
Okay. So initially, total angular momentum is just r cross p, or mv naught times v. That must be equal to the instantaneous angular momentum at this point right here, which is the rotational inertia I of a point mass times omega, the angular speed about r, which is this the phi 2. Phi is this angle here. This is the origin. So this is how fast phi moves. So then you can solve for r² and put it in to get rid of r², and magically the dt's cancel too, and so you're left with just integral over theta. And this integral is easy enough to do. So at the end of the day, you get a b. So you have an expression for b, the impact parameter, as a function of the angle theta. So now you know if you're some ways above the axis, then you'll be scattered at a certain angle, right? So that's great. That's not the our task, though. Our task is to find the differential scattering cross section, which we had d sigma over d omega, which we had rewritten in terms of derivative of b expected theta. And so we did this, and after all the smoke clears, you get this expression. This is where we ended last time. It goes as 1 over the energy squared and 1 over sine to the 4th of the angle, the scattering angle divided by 2. Now, rarely do you have anything to do with going to the 4th power. First of all, the energy 1 over the energy squared. That's kind of easy to understand. You saw in the demo that the faster the ball went, the less deflection. So That means less interaction time, less chance for it to be pushed. If it goes slower, then more chances, you get more scattering. Now, what is this sine fourth to the theta? What does that look like? So we go like this. Sigma d omega equals KQ1 Q2 over 4B squared 1 over the sine to the fourth theta divided by 2. So theta 0 corresponds to no deflection, no scattering, straight moving straight. So we plot theta versus d sigma over d omega. So at 0, what does this function look like? The sine of 0, 0, 1 over 0, infinity, right? So it's super big here. And then as theta is going to range from 0 to what? Pi. To pi, right? And so if you put in for pi, what do we get? Theta goes to 0, infinity. And then what is the sigma, the omega? Is it a value at 180? What do we get? Yeah. I put in pi. Yeah, that's sign disappears, right? So it's just going to be some constant. Right? So some constant. So it's going to go somewhere like this, and then the value at 180 degrees. So it's going to look something like that. What's called the backscattering event where it gets scattered 180 degrees back, it's not 0. It's a finite value. And if you think of this as a distribution, most of the particles will be deflected at lower angles, smaller angles, and then a very small probability of getting deflected by 180 degrees, but it's not 0. Remember the hard sphere scattering case? What was that? That was just a constant, remember? Hard sphere scattering is, so this is Rutherford scattering. And if we're going to compare to hard sphere scattering, it was just a constant. So anyway, why is this important? Well, back before the 20th century, we knew about the atomic model about atoms. We knew that it's made of plus and minus charges, but we actually didn't know how they were distributed, okay? It was not clear how the plus and minus charge, now we know it's the, nucleus is positive, electrons are moving around, and if for scale, if for a hydrogen atom, if I have it, the proton here, you know how far the electron would have to be to scale? About a kilometer away, right? So an electron would be a kilometer away. So now we know that, but back then we actually didn't, and there are many theories. Let's see. Shit. Okay. One of the theories to kind of one of the theories I was contending at that time is called the plum pudding model, where basically the positive, it's the positive charge is in a cloud, and the negative charge, the electrons, are small and tiny. So this plum pudding, because it's like the big, I guess those are plums, I don't know, but the little morsels are inside the whole cake. So if this was true, how would it affect a scattering event like this? Okay, before we derive this 1 over sine to the 4th theta over 2 law, one charge, one positive charge, isolated, right? But now we don't have to redo this because the positive and negatives are together, right? You have a positive kind of distribution, weaker distribution followed by a negative, and it's kind of basically not going to give you this distribution because you can see that sometimes you might be attracted by the negative charge, right? And then the positive charge is not like a hard event. It's more, it's kind of smeared, and so you won't get that sharp kick backscatter, right? Remember the backscattering because you're hitting it head on, boom, get back. But now if the positive charge is smeared around, you're not going to get that kind of event. So this is what Rutherford wanted to do to test the distribution of charge inside the atom. He used basically what we just drew here. He took a positive charge and fired it at atomic atoms and see what their scattering distribution was, to measure their scattering distribution. So this is the Thomson model. You put in you fire what are called alpha particle source, radioactive source that emits alpha particles. Alpha particle is the bare helium nucleus, so it's positive 2 charge. You shine it at a gold foil, and because of the plum pudding model, the positive charge is distributed, you won't get the back scattering. We did Rutherford scattering last time and showed that you would get back scattering events if the charge was like a hard sphere kind of thing, one place. But if in the Thomson model, the positive charge is distributed this way with all of the things, so you won't get these scattering events. And what was observed though is not that you do sometimes get backscattering events that fire more than 90 degrees back. And it supported the Rutherford model very well. Rutherford model positive nucleus is more localized, smaller within the negative charge. And this is a quote from Rutherford. It was quite the most incredible event that ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back. The alpha particles are very big and massive, and so we say once in a while this really energetic and massive particle gets sent back. Right? And that was amazing. So here is the distribution of Rutherford scattering again. Impact parameter B, right? And so get closer and closer down, boom, back scattering. And here's the thing we just plotted here on the board. Michael, you're seeing the PowerPoint, right?
Yeah.
Okay, good. Okay, and then here's the experimental data with here. Fits it very nicely. So this is a bunch of experiments. Yeah, calcium being shot into argon, terbium being shot into lithium, so forth, so on. I don't know what it's or something argon, but you can see that the data fits the theory fits the data very well.